all the material. So you can contact me at any moment after the sessions through my email address. Do not hesitate to do that. But as I said, all the material of the lectures are available online. I'm going to, in a minute, put the link to them in the chat so that you can click on it and start having a look. And I also have a Slack channel that will be open all the time. So at any time, if you feel comfortable with it, you can contact me, and I normally respond very, very fast. If you feel that for some reason I'm not responding, please do not hesitate to insist, because your email might have get lost on the spam, etc. I get a lot of mails, but normally I respond very fast, so do not hesitate to interact. The interest with Slack is that you can not only interact with me, but with other members of the course. So this makes things more friendly. So, but it is on your convenience whether to use Slack or not. So, well, these lectures provided by myself are part of the ICT course that you have, and we will address data-centric or a data point of view of smart grids and smart cities and smart energy. And the idea is particularly to let you be aware of course, of the importance of data. I do not think that I have to convince you all that data is important, that it is at the center of many solutions in industry and in academia. But anyway, I will try to introduce to you the profile that we have today with respect to data. And then, of course, a lot of associated tools that let you exploit the data to solve problems that you address in your professional life. So this is the general idea of these sessions. And as I said, we will touch to many different technologies. So be patient with respect to technology. You might be feeling that we are just going back and forth to many tools, but the idea today is that particularly when we design data-centered solutions, we have to be acquainted with different technological tools in order to get as much profit of the data. Officially, my sessions are intended to talk about big data. Well, the last 10 years we've been talking about big data. Today we rather talk about data in general, and we focus it from the data science perspective. So of course, I will have some words with respect to big data, but you will see that we have moved towards more data science perspective and experimental perspective of data. And this is the point of view that we are going to address in these sessions. So as I said, I'm going to start with some administrative information so that you make sure that you understand the principle of the lecture, the way we're going to work together, and that you can perform all the activities proposed during my sessions. So first of all, the general objective of these two theoretical lectures and then some practical sessions that we will have afterwards is to describe the principles of the new emerging data science. Okay, so data science is quite new. Many things are being said about it, and the idea is to have a kind of stable basis of what it is and what it how can it be used in your domains. So the idea is that data science is in fact an experimental science. So we're going to do experiments using digital data. Okay, and the objective is to teach to apply method and techniques for analyzing data collections through experiments that will run on big data analytics environments. Okay, so the key concepts here are, of course, data collections that are available in open settings, design experiments, and all this, of course, is digital. So understand how we can use computing-based environments in order to run our experiments. And what for? Because we want to use data to analyze situations and phenomena. We want to model phenomena happening in different environments, and in the best ideal situation possible, we want to be able to predict the behavior of environments. Normally, when we apply data science and this kind of perspective, it is because we want to analyze what we call complex systems. So systems that can be described, its behavior can be described using many different variables, that it is very difficult for a human being to tune all these variables and understand the way these complex systems work. And this is why we need computers, we need algorithms, and we need technology in order to try to, as I said, analyze, model, and predict the behavior of these complex systems. So what are you going to expect at the end of the lecture? Well, you have to make sure that at the end of these sessions that we will share together, you will be able to design and implement data science experiments. Okay, so if someone afterwards comes with some bunch of data representing phenomena from a smart something, an environment, or whatever, you are able to take this data and then design some experiments in order to answer research questions. Okay, so the key here is that I have some data, I have some research questions that I want to answer, and then you, as data scientists, are able to get this data and design an experiment that will be intended to solve and to answer the research questions. Okay, so this is what you have to make sure that at the end of these sessions you are able to do. Okay. And then normally research questions, as I said, are related to analysis, to modeling, and to prediction. Okay, so you have, of course, to make sure that some human-defined research question, you can interpret it and then decide whether you are addressing an analysis problem, a modeling problem, or a prediction problem. And out of it, design the corresponding experiment and exploit the data in order to partially or totally respond these research questions. Okay. So if we decline this general learning outcome, the idea is that you have to understand theoretically and technically the steps of general data science processes. Okay, so now at this historical moment, data science has consolidated, and so there are official procedures and processes that are provided and are the basis of this new science. And the idea is that you get introduced to them, you get acquainted to them, and that you feel comfortable applying them to design your experiments. Then, of course, if data science has emerged and is solid now, well, there are many tools, as I said, that can be used in order to design these experiments. So the idea is that you know the tools. Of course, since there are many different solutions, you will not be comfortable maybe with all the solutions, but the idea is that you have a general perspective of the available tools, because I suppose that in your professional activity and in your projects, etc., what you will have to do is make decisions on which are the best tools to be used in order to run your experiments. So the idea is not to touch every tool, but rather to make sure that you know the characteristics of the different tools, and you get the reflex to make decisions to choose the tools. Okay. So this is a second aspect that you have to make sure that you get out of the sessions. And then it's the same with the techniques that you are going to use to resolve the research questions. So how are these techniques materialized? Well, in terms of algorithms. Okay, so the idea again is that you are acquainted with the families of algorithms that are available today. You have many different libraries with these algorithms implemented, but you have to choose the algorithms and then know how to play with the parameters in order to solve your problems. Okay, so this is another aspect that you have to make sure that you get out of the sessions. And then, of course, know how to use the experiments and your experimental results in order, in fact, to make decisions. Okay, depending on the type of experiment and of the results that you get, there is a lot of interpretation involved. Of course, here you will have two hats. You will have the hat of the data scientist that designs the experiment, but you are acquainted with the problems because the problems will touch energy, will touch cities, will touch buildings. So you are experts on these topics, and there you, with your expertise, you will be able to interpret the results of the experiments and help you make decisions out of these results, or even decide that the result of the experiments are not representative at all, and that you have to design them differently, and in order to get some output out of them. Okay, so these are the learning outcomes that you should expect out of the lectures. Now, with respect to the content, well, we are on the introduction now, so we are going to define data-centric sciences, that are those sciences that rely on data science in order to design and run experiments. We will get acquainted anyway to digital data collections and their characteristics, because their characteristics will drive the way experiments will run and eventually get out of the lab and deployed in real conditions. Okay. And finally, we will profile data science with respect to data, to analysis, and to algorithms and tools, so that you have the fundaments to start addressing experiments. Then once we have this will be normally this session more or less. Then we will start introducing how to design experiments. Again, understanding the life cycle of the collections. Of course, you can imagine that an experiment is not something that you run once in a time and then you are happy it's over, because data and data collections themselves are living elements. So new data come, new input comes, and then you have to decide whether the results out of the experiments are still valid or not. So there is a kind of life cycle, continuous life cycle on the experiments. And so you have to design also the way these experiments will run recurrently or redesign recurrently in order to exploit new data coming or even new results coming from other experiments that will feed the knowledge you get out of them. Well, since we are using computing science in order to run the experiments, you will need to know which are the architectural possibilities that you can use depending on the moment you are with respect to these experiments, okay? Because experiments are nice, but normally at some point we want to make them become solutions that can be used in real conditions. And this evolution with respect to starting some testing, then doing experiments in laboratory conditions, and then going towards real conditions. This requires different computing resources, and you have to know which are these resources and how you can use them in order to make your solutions evolve. So this will be a second big content of this lecture. And then we will touch practical examples, okay? So what are the tools, the theoretical tools for data science? This is not new at all for you because you have an engineering education. So nothing new. There's a lot of statistics involved. So we will call to your knowledge on statistics, particularly on descriptive statistics, in order to design some type of experiments. So the idea is that through examples, we will see how these descriptive statistics can be used in order to deal with the data and design our experiments. Then another aspect of statistics will be statistical inference. Again, you are quite acquainted with this. This is your engineering education, so nothing new. The only thing that will be new is how to apply it and build and design these experiments and hopefully drive solutions out of them. And then maybe, even if today I will be surprised that some of you are not, have not had the opportunity to go towards machine learning and to artificial intelligence, but maybe something that is new and that at least is not fundamental knowledge from the engineering part is how to use machine learning and artificial intelligence to solve problems, and which type of problems, and how do we do this with this more computational perspective. Okay, so these will be the three main practical examples that we will use in order to, again, understand and learn how to design the experiments and answer research questions. Okay, so it seems a lot, but do not get afraid. I mean, examples are there normally. Another aspect that that you have to consider, I know that you have many different backgrounds, and that probably you have many different programming skills. So I will not ask you to be geeks, completely geeks on programming with advanced programming skills. We will rather go through examples well prepared so that you still have to do some coding, but very few, and rather concentrate on the design of the experiments, as I have explained before. So anyway, you will see that we'll have a lot of help and material if you do not feel very comfortable with programming. This doesn't matter, because what you will have to be comfortable with is on the experiment itself and of course on the interpretation. Now, with respect to the organization, well, there will be two magistral theory sessions. Today is the first one. It's 4-hour sessions. And so it's today and next Monday. And then eventually, but this hasn't been established yet by the school, there will be practical sessions. And there you will be divided into groups. We will announce to which group you are going to belong to. And then there will be 3 sessions. The sessions are the same content, the 3 of them, but in smaller groups, we will touch the practical material, even if, as I said, for those that are arriving now, is that even in theoretical sessions, we will touch a little bit of practice so that you can touch the ideas that I will be introducing theoretically. And of course, there will be some evaluation aspects. So what will happen is that since you're going to do a lot of practice, there will be a very simple practical project derived from the exercises that we will address during the sessions, and that will count for 40% of my grade. Okay, so the total course, ICT course, has different lecturers, and every lecturer evaluates his or her part, and the total grade of the course is pro rata with respect to the number of sessions addressed by each lecturer. So my part will be graded like this. Other parts of the ICT course will be evaluated differently. Okay, so it's a little bit weird for those that are not acquainted with the French system. We do things like that here in France. So you have 3 lecturers, everyone grades, and then we define a global grade of the same course out of these grades, and with different philosophies. Okay, so for my part, this will be this practical project, and then there will be a final exam, which is 60% worth. And the final exam, well, it's a kind of written exam. It happens online, and you will see that I will give some days in order to answer the exam, so that you do not have to a real final exam session, okay, since the lecture is happening online. So this is for these aspects. Now we are going to go through the material and how you can access to it. So as I said, you can use my email. I received your addresses today, your email addresses. So the first thing that we are going to do in the next part of this session is that I'm going to share a Google sheet, and there you will see your email address. In some cases, there is your name. If you do not see your name, please fill in the name. And then if you are using an alternative email address where I can contact you and that you read more often, please add it to the list so that I can be sure that when I do an announcement, send an announcement, a notification or whatever, you receive it, okay? So I'm going to stop a little bit of sharing this screen so that I can show you the sites and so on and so forth. So give me a second. First of all, what I'm going to do is I'm going to share them the address of the Google Sheet form that I kindly ask you to fill in with your name, first name, last name, and if the email is right, then you leave it. And if you want to add a supplementary email address, do not hesitate to do that. So there's first the Google Sheet that you can fill in while I am presenting other things. Okay, so please do, so that at the end of the session, I'm sure that I have a proper list of the students and that I can contact you. So this is the first thing. Second thing, as I said, all the material of the lecture is available here. So I'm going to introduce a little bit. Sorry, I'm using part of the time to make sure that you have everything you need, and then we'll start on serious things about data. Okay, so now I'm going to share my screen so that I can show you the site. So normally you can see the site. So the address is on the chat. So I'm going to put it again because those that are arriving afterwards do not see the previous messages. Okay. So first and then here. So if you go to the link that I put on the chat, where you will land is to the lecture site. Okay, so I named it Data-Centric Smart Experiments. Of course, you have context and motivation. That's an objective. This is not very important, but what is important is the content. Okay, if you go to the content, you have the PDFs of the slides that I will be using. Okay, sometimes I make some modifications. So after the lecture, I will update the PDF so that you can have the version that I used in your session for teaching the different aspects. Okay, so here you have the theoretical part of the course. Then, as I said, there is a lot of practice. So practice and practical exercises are in the hands-on section. So what you will land is with a lot of a big list of exercises and things to do. Of course, during the sessions, I will point you to the specific aspect to have a look to. And then an important remark is that at some edition previous to the pandemic, we used to use computers in the school, but then we realized that sometimes the data collection that you have to play with you are not allowed to have so much data in your school accounts. So what I decided is to dematerialize everything, and everything will be run online. So what you will need to run your experiments is a tablet, an iPhone, or a smartphone, or a machine, a very simple one, because everything will be run in an externalized manner. And this is practical, but this is of course important because many of the data science experiments are done like this. Okay, so this gives you the opportunity to see how people work in data science with experiments, first of all, and then it's practical because we do not have to install anything or whatever. Okay, so so this first part is no longer valid, but so this, and then afterwards it's valid. But do not worry, it's just I'm showing just the general overview of the site so that you do not get lost when you access to it. And of course, as I said, in every session, I will point you to the right thing to have a look at, so that you don't get lost. Now, of course, there are some readings that you can have a look at. So, but this is not a mandatory thing. This is just to give you background with respect to what I directly address in the content. And then, of course, there is a bibliography with more references that talk about the different aspects that we will be addressing. At some point, again, during my talks, I will point you to some on or other material so that, again, you are not overwhelmed with many different references to have a look at. And then last but not least is this knowledge control element. There you have the questions that you must be able to answer at the end of the lecture, okay? So I presented the learning outcomes, and here you have those questions that will let you be sure that all the learning outcomes are achieved after the sessions we are going to work together, okay? And at some point that will happen in an asynchronous manner. If you have questions on your answers and or on your understanding, you can make sure that, well, we can interact and you can make sure that you really got the message of the different parts, okay? And this is useful also because in order to prepare the final exam, you can go through it. Of course, this is not a questionnaire, so the direct questions will not appear in the final exam, but still this can let you prepare your final exam. So questions so far? Again, for those that have joined the session just some minutes ago, what we are going through is the site of the lecture where you can access to the material I will be using in my sessions, okay? So you have the link there, and at some point you can have a look. So I'm going to start sharing there. Again, if at some point in the session you have particular questions, do not hesitate and ask. So just to make sure that you do not get tired, we still have some time ahead for this first part of the first session. So I will stop at 3:20 and we'll give you 10 minutes break, and then we will come back for the second part of the session, because I understand that 4 hours with me only talking, at least in this first session, is not the best conditions we can ask you to support. Okay, so once we have set this organizational information, we can start with the content. So again, I'm going to share my screen and start with this first part of them. So in order to start talking about data, about experiments and how you can use them, we have to start talking about data-centered sciences, okay, which are their principle and their common aspects, okay? And in order to do so, we have to introduce the first important notion that you have to bear in mind, because this is the leitmotif of the content of this course, okay? And the notion is datification, okay? And datification is the idea that data is everything and everything is data. And once we say this, what we're saying essentially is that any environment in the reality can be transformed into data. Its behavior can be transformed into data, and it is possible to, out of this observation of these environments, do something about it. Okay. And of course, since these observations are digital, we can do something in a digitalized manner. Okay. And so as a result of this, we can say that we turn reality, phenomena happening in reality, into data. And this is thanks to the old big data trend that happened at least 10 years ago. Okay, so at the beginning of this boom of big data, which is the end movement regarding data in general, but anyway, so at the end of this boom, what we concluded out of this is that we can transform phenomena, any phenomena, into data, thanks to technology, of course, and that we can use these transformed observations, which are data, into some knowledge about these environments. Okay, and this is called datification. So to make sure to give a specific definition of datification is rendering into data aspects of the world that have never been digitalized before. Okay. So this is the part of novelty with respect to what we knew with respect to data in previous moments of history. Okay, and why can we do that? Well, you are all familiar with this because we have deployed sensors and devices that observe what happens in many different environments. Okay, and so these observers have let us produce the data that we can use and that drive datification. Okay, and what do we need this datification for? Well, we need it because, and what is special about this is that any individual can analyze this data, which is normally huge in volume, in short periods of time, and thanks, of course, to computing. Okay, and to do what? Well, to obtain analytical knowledge. Okay, and what for? Because what we have been doing before is that, of course, in experimental science less, but in the normal life, is that we used to make decisions empirically. And the idea with datification is that we will no longer make decisions empirically, is that we will use data, evidence, observations, out of which we are going to, well, of course, we are going to process them, out of which we are going to have enough insight about the environment so that we can make decisions. And this can happen in many different contexts. This can happen in our daily life as civilians going through cities. For example, if I want to make decisions on the best hour possible to go back to home and avoid traffic, I will use evidence, which is the evidence, the situation of the traffic, and then I will say, okay, out of this evidence, I know that the best moment in which I can go back home is at 4:30, because this is the moment where there is less traffic in the path that I'm going to use to go back home. Okay, so it's not longer empirical, it's out of the evidence, I make my decision. What is the best decision I'm going to make in order to decide whether to build a building in some part of the city, again, I will use all the data possible in order to do that. What is the best decision I can do in order to decide whether to subscribe a contract to an energy provider for home if I live in Grenoble? Well, I will see, and I will know that there is only one provider, and the only decision I can make is to use the only energy provider that there is in Grenoble. But if I'm in another city, I can decide which provider is best for the situation of my daily life, of my house, etc. Okay. So this is the kind of possibility opened by datification and the spirit in which it works. Now, out of this, well, there was a boom. Everyone wanted to use data and to exploit the opportunity of this kind of new paradigm, okay? So again, the new paradigm is not exactly the data, it's the possibility that any person can exploit the data. Before, it was only in data centers, in scientific environments, in industrial environments where people could do that, but not normal civilians. And now today it's for everyone, okay? And there were other sciences that haven't had the experience of this access to data, and that they started redefining their methodologies in order to use this movement. And it is how different sciences appear that we can call data-centered sciences, okay? So the common aspect of these sciences is that data collections are the backbone for conducting experiments. Of course, when we talk about data-centered sciences, as I said before, we are talking about experimental sciences, okay? So we conduct experiments, we drive hypotheses, and this leads to valid, under quotation, conclusions, models, simulations, and understanding. And it is very important that we understand that the validity of and the veracity associated to the results that we obtain out of experiments is not a general truth, okay? Because the observations that we do from the different environments are always partial. Even if I have huge volumes and huge amounts of observations of a specific environment or system, it will be always partial, okay? And so the conclusions I drive out of exploring this data is partial. But the good news is that I can estimate to which extent this conforms to reality, okay? And so with this principle, we have today social data sciences that we are very familiar with. If you use your favorite social network, you will see that there are parts of the site where you have retail announcements and you can react on them. And this is intended to understand the behavior of ourselves as consumers. And out of this, the companies make decisions on which products they can suggest to us and that we can potentially buy. So this is an aspect. Another aspect is security, for example. So out of the behavior of people, it is possible to determine which areas in a city are more secure than others, etc. Okay, so this is done by social data science. Then there is, of course, digital humanities. So all the problems that that we knew in digital humanities have been transformed into experiments, and so we can get knowledge out of it. Then there are other more trendy sciences like network sciences. There, the principle is that anything can be represented as a network. And the only problem is to choose the best network model in order to represent the environment and then make conclusions out of it. Example, network science has contributed a lot in the understanding on how the pandemic evolves across the world. And it helps making decisions to governments on which are the best, how the pandemic evolves, and eventually decide which are the prediction of the evolution of the pandemic, and then decide some public policies. And then there's also other sciences applying, again, mathematical models and on top of data in order to address problems. Okay, but all these sciences, including data science, are using this data as backbones. Now, what is the challenge? Well, the challenge, and this is where we come back to this lecture, is that we have to develop methodologies that combine data management. Of course, data cannot be used in its raw status. It should be managed. So we have to combine data management, algorithms, and normally from the computational point of view, algorithms are greedy in terms of computational resources. Okay, so we have to decide which is the best machine that we can use in order to run these algorithms, and also programming models that must be tuned in order to make our experiments run, as I said, in target computer architectures. So what is the point of this? Well, first of all, well, I've said data management. What is the issue there? Well, you have to decide how much storage space you need in order to archive your data, for example, for how long, and if you want to make it available, how many copies do you need to have in order to be sure that you do not lose your data. Okay, so this is the type of problems you address with respect to data management. And since the data is the backbone, well, you have to reason about the best way to manage this key element of your experimental approximation. Then the algorithms I explained already, and then programming models. In our engineering education, we are quite familiar with programming. But the programming paradigm that we learn is what we call a linear programming model, okay? So there is one control flow, and the control flow is one instruction after the other, 1, 2, 3. But the thing is that since we are touching greedy algorithms, so you might know that some of the algorithms, if you execute them like this, one instruction after the other, they can take an eternity in order to finish and get a result. So the alternative is to see that whether with other programming models, it is possible to run them in acceptable time, execution time. Provided the volume that we use, the volume of data that we use, and the complexity of the algorithms, it is in general mandatory to use other alternative programming models, and the alternative is parallel programming models, okay? Because we are going to distribute the workload in many different machines in order to get results in reasonable time, okay? So we have to learn these programming models, and then, of course, the result must run in some machine, and there are machines with a lot of computing power, And so, sorry. And so the idea is to decide which is the target architecture that we are going to use to run an experiment. Is it a classic PC or a personal machine? Is it a device, a telephone, a smartphone, and a smartwatch or whatever? Or is it a more high performance architecture that can deal with the problem? Some of you might be familiar with online gaming. And when if you have played online with these new games that have a very nice rendering, the problem with the rendering is that the system has to synchronize the actions of players with the nice rendering, visual rendering that you have. And this requires a lot of computing power. So there are special there's special technology called GPU instead of CPU, GPU, that has enough power to parallelize the visualization of the rendering so that you have the impression that everything runs in a very smoothly manner. Okay, so there, these GPUs are intended to run the visualization in a way that you have the impression that the game runs in a very smooth manner, for example. Okay, so this is not only for gaming, there are other applications in which you need this type of quality of execution. And so you might decide to use this kind of solution. Okay, so these are the elements that have to be synchronized in order to design solutions. Some of them are now transparent to the person that designed the experiments. Others are not. Okay, so at some point, in some situations, we have to go down to the details of architectures in order to run our experiments. Okay. Now, once we have said this, then the question that comes up is the objective of the experiments. Okay, so if we are going to design experiments, okay. So I have questions. Not exactly. Okay. So it is very useful to classify the type of experiment that we have to design, because that guides us in the way we are going to design it. Okay, so there is a kind of spectrum of the objective of the experiments that we can consider when we deal with data and with data science methodologies. So in the horizontal line, you have the type of algorithms that you can use according to the different experiments, and then let's have a look. The type of experiment is guided, as I said at the beginning of the session, with respect to research questions. So there are essentially 4 types of research questions. When my research question is intended to understand what happened, okay, in which conditions do I have accidents at the entrance of Grenoble? Okay, what happened? So the idea is that we are in fact looking for insight on specific phenomena, okay, produced, for example, in the city, no, in the road. And what we are looking for is to provide information. And normally, this type of questions are solved with statistical methods, okay? So just by using statistics, normally descriptive statistics, it is possible to answer this type of questions. Then we can have more ambition in the questions we want to solve in an experiment, and is why did it happen? Okay, so there I am looking for diagnostic analytics, and there are many solutions associated to analytics that can help me with it. I can use statistics, or I can use models coming from artificial intelligence and from machine learning, or even from other mathematical disciplines that can help me respond to questions of the type, why did it happen? Why did some event happen? And when I'm there, I'm in the middle of hindsight and insight about some situation. Then I can go further and ask myself about questions like, what will happen? So this is prediction. So I'm performing predictive analytics. And well, here I announced machine learning, but out of your engineering education, you know that there are mathematical tools that help me to answer predictive questions. And this is, for example, regression. Okay. So regression, the family of regression models can help me to predict some situation. But there are cases when it is not possible to apply regression. Which are these cases? When the data do not cope with the requirements that regression models ask me to have in order to apply them. For example, in linear regression, you remember from your education is that the variable that you are going to predict has to be linearly independent from the other variables. And if this is not the case, either you work with the data, but if you cannot really work with the data because of the status of the data, of the quality of the data, then it is not possible to apply this kind of model. And so machine learning comes into the arena, and there are some models out of machine learning that are less restrictive with respect to the quality of the data and the properties of the data that you must verify in order to apply the model. Okay, and so you can use them in such situations in order to do prediction. And when you are there, you are on foresight research questions. And then the most ambitious thing that you can expect is to answer questions like, how can we make it happen? So I want to reproduce some phenomenon. So I have enough knowledge about the event and the phenomenon so that I am able to reproduce it. Okay, so there I am in the arena of prescriptive analytics, for example, in order to solve optimization problems. And there, again, there can be some complex mathematical models that I can apply, but today it is often common to apply some artificial intelligence models that can help me to do this. Okay, so this is the spectrum of research questions that we can address using data science. And these are the types of families of tools that I can use in order to answer to such questions. And as I said at the beginning of this session, the objective is to give you the elements to make decisions on, of course, identify the type of requests, because normally it is not direct that you know whether you are going to, you want to answer one thing or the other. And then according to the data, which is the best possible model and tool that you can use in order to answer it, okay? So it's a very generic overview, but this gives you exactly an overview of how to organize yourself in order to start addressing this experimental exercise. Now, once we are able to do this, what are we going to use these experiments for? This is just the publicity of the importance of data science and its experimental methodology. Well, when I want to understand the behavior of business networks, as I said in my previous examples, all retail companies do this. They recommend us with products. Netflix, for example, recommends us with possible films or content that we might be interested in. Uber Eats and so on and so forth, the type of food that we would like to eat according to our behavior. So this kind of questions, if you are, of course, a company and you want to address target market sectors in order to put your company forward. So this type of experiments might help you, again, make decisions on which is the best strategy to adopt in order to make your company get a better profit. Then again, publicity is another application. The way our devices work now today, as devices have become more and more smart, the way we use them can help the device modify its behavior so that it's we have a better user experience out of this. This happens, for example, with with Alexa and this kind of devices, that it adapts to your voice, to your accent, etc., so that it learns out of your behavior how to adapt its behavior so that you can feel more comfortable. So these kind of things. And then, of course, other things like more administrative, the way our email adapts to our profile and our behavior, voice recording, etc. So these kind of applications are common applications in which the results of data science experiments can be used. Of course, the debate here is not whether this is glorious or this is possible. This happens. And so, and these are the type of applications that data science is being used for. Okay, so ethical and other problems will not be addressed here, even if I declare officially that they are important and that they should be discussed when this kind of solution is adopted. Okay, so what we're going to do here is learn how to do such kind of experiments. And so, well, I got you introduced in a very general manner of the use. So these are the sciences. And, but since the backbone is data, well, we need to profile this data, okay? What are we talking about when we are dealing with data, and why is it so key and critical to know how to manage it? Well, this is the result of the big data trend, okay? So at some point, people decided that we were able to access a lot of data, and they called it big data. And big because of the volume, even if the volume has never been a problem in computing science, okay? We have invented every time more storage support, more computing capacity, etc., to address new volumes of data. So we went to the moon with 64K, and now we are going to Mars or out of the Earth with teras or more than that, okay, of data. So this is not a problem. But what the lesson, if you want, that we came out of with as a result of this trend was the properties that we have to be aware of regarding data in order, again, to decide how to design our experiments and how to exploit it, okay? So there are 5 main properties that we can attach to data, even if then people started to invent more properties. But these are the 5 fundamental that we have to consider, at least for classic experiments. Of course, there is the volume, okay? So there will be always more and more data. Just for your general culture, at some point, some years ago, there was a group in the United States and then here in Europe that started to figure out whether the measures used in order to measure the volume of data were adapted to the volumes that we are starting to deal with. And so they said that, in fact, these measures were not enough, and they started to introduce notions like brontobytes or geobytes, which means thousands of yottabytes and thousands of brontobytes, etc. So huge reference to huge, really huge volumes of data. So anyway, this is to say that volume plays a role in the characterization of data, even if it's not that it doesn't determine a lot the complexity of the data. Okay. Then another maybe more important and critical property to consider about data, it's what we call velocity. Velocity is the rate in which data is produced. Okay. So maybe you're not producing a lot of data, but it's produced constantly. And this is a big challenge. Okay. So velocity is maybe today is the driving property of experiments, because everyone can do experiments out of postmortem, even if voluminous data collections, but doing experiments online and interpreting a phenomenon online, this is a challenge that is currently being addressed. So there is no solution for this, okay? So velocity is a very challenging property that we have to be aware of when we want to ask research questions and build experiments. Then another property is variety. As I said, when I described this datification story, I said that there are many devices producing data. And some of the, each device produces data in different formats. Some of the formats are open formats. For example, in images, JPEG, GIF, etc., are formats that any computing environment can interpret. But there are cases in which the formats are not open, so you need specific software in order to interpret the data. So this variety of data makes it difficult to treat data in the same conditions, okay? And you have to provide solutions for this. But if we are talking about data that is produced at a high rate and that there is a lot of of data, this transformation and this required due to variety is very challenging, okay, because it takes resources. The idea is to try to deal with this variety. Normally, and this is something that we learn again in our engineering education, when you have different elements expressed in different conditions, what you do is transform them and express them in the same terms as a pivot representation. And this was a very common solution during some time to address this variety problem. But when you have a lot of big velocity and big volume, this is not very practical. Okay, so there are other solutions to deal with variety. So then the fourth property, this is very important, okay? If you are sleeping now with my talk, here, wake up and keep track of these properties, because this is key for the rest of the content of the lecture, okay? So now veracity means that the validity of the data, okay? Normally what happened, if you have learned, for example, to use the relational model and relational solutions, consistency is a very important property, and it says that you have only one truth about the data, okay? The problem is that if you are observing data coming from different devices, you can have different observations of the same object. For example, if you are observing the temperature of a room out of sensors, and you install sensors in the entrance of the room, close to the lights of the room or close to the windows, you will have different readings of the temperature of the room, and all the readings are fine. It's just that the conditions in which they are collecting data is different. Okay, so veracity is not one. You have to aggregate these different true observations and decide which is a general conclusion out of, for example, the temperature of the room. Okay, so in order to deal with this, you have to define techniques in order to define the degree of veracity that you are asking from the data and that you are going to process and compute out of the data, okay? And then last but not least, there is value, okay? So we have learned that data is associated with economical value, okay? Those that use streaming solutions know this. We buy data, we buy songs out of some economic model, okay? If I want to access to content continuously and without publicity, I subscribe to this type of access. So data has economic value. And if I'm on Netflix, or if I want to access to multimedia or media content, there is also a cost, and there are different, I access to this content in different conditions and I pay for it, okay? So determining how much is your data worth is very important, okay? Because if you are a company, if you are an organization, you are producing data and you have to know how much does it cost to deal with this data and to manage this data. And if you are going to share it with the world, how much you are going to tax the world in order to access your data, because you have paid for it, okay, for managing it, for producing it, for collecting it, etc. Okay, and maybe it's the first time that value, economic value, has a big importance, not only related to data, but also related to the infrastructure you use in order to exploit the data. And you have to measure it in order to know the economic cost that implies doing an experiment, responding a research question, maintaining the question, maintaining the experiment, etc. Okay, so when you go to ICT real conditions, the value is a critical element to be considered when you are going to deal with data. Okay, so a very important thing to do. So we have the profile of our data. And then in order to, as I said, to start digging into the data science, there are two elements that have to be considered: computation, which means algorithms, and then experimental settings, which means architectures, which means computing environment. And if you combine the three and you answer to some research question of a specific discipline, then you are there in the core of the design of data science experiments. Now, just to, again, for your culture, there are now professional profiles related to this. People that address these mathematical models adapted to answer specific research questions, as the experimental questions that I introduced in the previous slide. They are called data scientists. Okay. Is it possible to apply statistics? Which type of statistics? Out of samples of data, how to identify the samples of data, how to use the whole collection, etc., and so on and so forth. So these people, or whether statistical models are not applicable, and then go to artificial intelligence or machine learning solutions. So these people that deal with the problem related to data and the models are called data scientists. And then people that translate this solution into a concrete running experiment that deal with the computing resources and how to prepare. It's like preparing an experiment in the lab, which is the infrastructure that you are going to use in order to prepare your experiment. So these type of decisions are done by data engineers. Okay, so these kind of profiles have emerged and are being asked, are being promoted in companies and in many different sectors. Okay, there are other profiles like data steward, you know? So which are the data that the company is going to produce, keep, in which conditions, which is the data that we are going to share. Is it ethical to maintain all this data or not? So these kind of things are decided by a data steward. So these profiles are emerged. So this is just for your cultural background. So as I said, this is related to the experiments. What time is it? Okay, we're almost there. 20 minutes and then a break. Once we have understood this, we can have questions. I don't know if you have questions, reactions, or something to say with respect to this introductory part. For those that are arriving late, I promise that it will be a practical session, but today I'm introducing things, so I have to keep talking a little bit, and then you'll see, you will get the opportunity to have more practice and less listening. So, and again, for those that have arrived, we shared a link where I am asking you to make sure that I have your email address, your full name, and if you have an alternative non-institutional email address, that you can share it with me, so that announcements, information, and so on and so forth can reach you properly. Okay? So that is one thing. And the second thing, I also shared the address of the site where you can access to the material that I'm using in this theoretical and then eventually in the practical sessions. Okay. So if there are no questions or reactions, I am going to start digging more deeply into the data. So I'm going to stop sharing this and then share introduction B. Then maybe, yeah, maybe before the, after the break, we will do some practical thing. So I have to share my screen again. Okay, do this like this. So that was the overview. And now I'm going to dig more deeply into the characteristics of data, because this is important. And then we will move forward to more functional things like algorithms. Okay. So, yes, well, you have the address also here, but again, you have it in the on the chat. And I also said at the beginning of the session that there is a Slack channel. What I will do is I will send you an email using the email addresses that you have put in the Google Sheet, and I will communicate about the Slack channel if you want to use it to interact between one session and the other and ask questions or whatever. So, data. First of all, we have to be clear about what is big data, okay? Since it's at the in the background of what is data science today, okay? So normally, big data is data collections with characteristics difficult to process on single machines. So that's the first thing. So if you have a machine, a data collection, and it doesn't work in your machine, it's because you are poor in computing resources. It is not because you have big data, okay? So it must be data collections that have to be absolutely distributed into many machines, and for which traditional databases are limited. Okay, so it's reaching the limits. If you reach the limits of existing technology, then you're talking about big data in terms of volume. Okay, if not, it's just that you have to buy more disk or buy more computing resources in order to be able to deal with this. Okay? It's not big data. So it requires new generation of tools, methods, and technology in order to collect, process, and analyze them. Okay. So now, since we are after the trend, some of the tools are here, okay, and the methods and the technologies, okay. It's just that you have to make sure that you really need such tools in order to deal with your data. And of course, it imposes, so the characteristics of your collection imposes the use of parallel processing and distributed storage. Okay? And there you're in this big data arena. So that's important to consider, okay? So that you do not say that you have 1 tera in your machine and that you are dealing with big data. This is not big data. Again, this is a nicer observation of the properties. Again, volume, velocity, variety, and veracity, and value. Since we are not touching the business model aspects in this, in my sessions, I didn't include volume, but value, sorry, but it should be there in your minds. These V's are called the the V models, okay? So for acquiring the jargon, so the vocabulary related to these big data and data science stories, you have to be aware that the properties used to describe big data are defined in what we call the V model, okay? And the V model has evolved. Now we are in more than 10 Vs, okay? So V is because all the properties begin with V. So there's volume, there's velocity, there's variety. So at the very beginning of the story, we had only 3, then we evolved into variability, which means inconsistency by constant meaning changes. And then there's veracity and value and so on and so forth. So the 10V was reported in this article of Jagadish in some years ago. Now you have 20 sort of whatever V's you can imagine with V's. And the only importance, as I said, is which are the V's that characterize your data, and which are the strategies that you are going to adopt and the tools you are going to use in order to deal with them. This is just a guideline for this. And again, how big is your data? So here, for those that do not remember the measures that we use for measuring the data, you all remember that it starts with the bit. And then we have bytes, which are 8 bits. And then normally, well, here you can react, because you remember that is with respect to a binary representation, so it should be 2 to the power of something, but here it is more democratized, and it's not talking about in a binary reference, but anyway, you have meaning that it should be 24 bytes, okay, but here is just making reference to the decimal system. So you have case, and here you have the jottabytes, the famous jottabytes that I refer to in my other slides, which is this size. And as I said, so there is a movement in order to have aggregated measures of the data. And if you are interested in reading why and which are the implications, this has implications in technology. We have to invent new machines and new storage technology in order to deal with this. Okay, so the first time that this notion of brontobyte and geobyte, etc., was referred to was in an article from the IEEE that is called Beyond Just Big Data, and says the importance of the notion of data, etc., and why does it call for new ways of dealing with this. And they conclude that anyway, in the future, in that future, which is some years ago, we were going to deal with hell of a lot of data. Okay. Now, what is important is once we have profiled the properties of the data, the important thing is when we want to manage the data is to understand that the collections have a life cycle. And each phase of the life cycle requires technique, requires technology, and requires strategy. Okay? And this is what we are talking about. First of all, we have to harvest the data, and the data normally, as in any harvesting situation, might not come in a proper manner. It might come dirty, okay? And so once we harvest it, we have to clean it. Example of this, you are all, due to your professional background, you are all acquainted with the fact that when signals are produced, they there might be errors, okay? So if you're harvesting from sensors or from smart meters, etc., the information might have a problem because of electricity or whatever, and there you have litter inside. And it comes like this when it's directly harvested and in its raw condition. And so there is a process in which we have to clean it in order to make it exploitable for answering research questions, okay? So this harvesting procedure has requires technique. Which is the technique? Of course, we have to decide which is the technology that we can use in order to harvest the data. Of course, if we are dealing with sensors, it's how many sensors, where to install them, which is the technology, what is the possibility in which they can get damaged, or they can derive because of some reason. And this harvesting strategy requires a lot of design, okay? Again, cleaning the same. Are we going, if there are missing values, for example, are we going to extrapolate and out of previous data, and we are going to fill in with extrapolated data, the data that are missing, or we are just going to impute and do not consider data that is has some problems, missing values or strange values or whatever. So these strategies must be defined, and they are defined depending on the discipline and on the type of data, okay? So what is reasonable to do if I'm using, for example, if I'm observing the electricity or the energy consumption from a household, and suddenly I see periods when there is no energy consumption. Am I assuming that people were out and they turned off all the consumption, or am I assuming that there was some problem and the data was not transmitted? And is it reasonable to, out of the behavior of the previous days, to estimate an energy consumption from this household, okay? And it's not the same from a household, out of a building, or whatever, something else, okay? So harvesting. Once we have harvested and cleaned the data, the question is, where am I going to archive it? And am I going to preserve it for how long? Is it reasonable to preserve it forever? And what does it mean forever? Or at some moments, am I going to get rid of it, or maybe put it in a cold storage and just keep part of it? And according to this, which is the technology that I'm going to use. For example, if I'm going to use the data that I harvested and cleaned regularly, I might use, for example, a classic database solution, okay? Either a relational, either a NoSQL, whatever, okay? Distributed or not distributed, but I can imagine this. If it's data that I am harvesting and cleaning, but I'm not using recurrently, I might just archive it and zip it or wire it in some way, and then put it in some cold storage support, okay? And there is technology for this. For example, there is technology based on the ADN on crystal solutions that is good for just cold data storage, okay? If I'm querying, this is not a good option because the retrieval time is very high. But if I'm just archiving, I can use such kind of technology, okay? So preserving, again, requires method and requires maintenance strategy and decisions on top of which I'm going to adopt some solutions. And you have guessed, in an organization, we have everything. We have data that we are using recurrently. We have historical data, and if I'm keeping the history of my organization, I might need to have cold data. Okay, so I need a spectrum of preserving solutions in order to deal with the different types of data that my organization is using. And then again, when I'm going to want to exploit it, at some point I might use only the recurrent data, but if I want to learn out of history, then I might use some archives, okay, and decide which are the parts of archives that I'm using in order to exploit the data. Okay? So preservation is these kind of problems that need to be addressed. Then, of course, I'm going to use the data. So in a second, we will see the different ways in which we are going to use the data. But anyway, I might need to process the data in terms of analytics perspective or aggregative perspective. Okay, so again, I need to define which are the workflows that I'm going to design in order to process and analyze the data. And these workflows, again, will depend on the way I want to consume the data. Okay, I might be consuming the data for decision-making that it's not critical. So the workflow will be completely different as if I am using and processing the data in order to make critical decisions. Okay, for example, in the stock exchange. In the stock exchange, I have to make critical decisions, otherwise I will lose money. Okay, so the way I am going to process the data will be quite different as if I want to decide, for example, whether I am going to agree to loan some money to someone. Okay, maybe for the person the decision is critical, but for me as a bank, I can take my time. Okay. And once I have processed and analyzed the data, I am going to exploit not only the data, but the results of the data processing and analytics. Okay, how am I going to exploit it? Is it going to be a one-shot exploitation? So I process, I analyze, I have a result, and I make my decision? Or is it that I'm going to deploy this process within an application? For example, the applications helping us, like Waze, for example. I'm going to go from home to the school, and I need to decide which is the best road to take at 4 o'clock. So the application is the solution, the decision-making solution and the data processing solution is deployed in the application so that every time I want to compute a trajectory, it provides me with an answer. Okay, so this kind of exploitation must be considered, okay, in this phase. And of course, this is a cycle. So when I exploit, I might produce new data that should be harvested, cleaned, and so on and so forth. And so this cycle is continuous, it's a cycle, and must be considered in the way I deal with my data. So now, once we have understood this, then we have to consider two main paradigms that we use in order to deal with data, okay? And this has to do with the type of data that I harvest and I process, etc. Okay. So until maybe the beginning of this century, the use of the data and the type of data that we used was data representing organizations and produced by the life of the proper life of the organization, but it represented the organization itself. Okay. So in this perspective, what we did is, for example, I want to deal with the data of the students of the school. So I know that I have information about the students, the programs they follow, the lecturers that teach in the school, the rooms of the school, etc. And so I model this kind of mini world, and then I feed this representation with concrete data. Okay. So the idea is that we model the mini world, the data represent facts. The data normally is structured according to some data model. For example, I can decide that in order to represent a student, I am going to have a last name, a full name, an ID, an email, the program she or he is inscribed in, the number of credits that she has studied, etc. So these are facts that I represent in a data structure because I'm using the computer, and this data structure has its constraints because it belongs to a data model. And once I have it, what am I going to do? I am going to query this information. And the query is precisely stated in the terms of, including terms, and maybe I'm going to use some operators. For example, how many hours in average is a room in the school used by master students? Or how many courses or credits does a master student learns in the first semester? Things like that, okay? So these are facts that I have stored in my information and that I retrieve. I could also use terms, give me the students' information of students coming from Brazil. And so I have a lot of them. And I can put some constraints, for example, the fact that students come from Brazil or not, but these are clear, simple, direct queries that I ask on top of facts. Okay, and the results, well, is a collection of items that completely or partially correspond to my requirements, so the expression of my query. Okay, and then of course the information can be distributed in many disks, are here, or they can be stored in data services like Google. If I query Google, Edge, and I don't know, Chrome or whatever, not Chrome, whatever, Yahoo. So there are services and I get them, but anyway, this is the spirit and the paradigm that I use. And we are all acquainted with this in our day-by-day life. Here I have an example regarding a hospital, a medical example, so I can have information about clinic, orders, departments, etc. And the information, as I said, is provided by the organizations. And for example, if I can ask about the number of patients with the diabetes, followed by a specific clinic or the vital signs, etc. Facts. But I can have another way of dealing with my data. I can have data that in fact do not represent facts, but represent observations, okay? So we observe phenomena, and these observations build a data collection. Okay, normally they are described as series of features or attributes. Okay, so for example, if I'm observing the energetic consumption of a household, I can see the hour of the day in which I did the observation, the number of watts, etc. Okay, attributes like this, and this series I can observe and I can produce during the day a lot of observations like this. Okay. So what does it change? Well, the possibilities that I have to query the data are completely different. Because when I do this, what I do is my objectives are analytical. I'm looking, as we said before, for insights or foresights of hidden in this data collection. And in order to answer this type of questions, I can no longer write an expression and then expect to have a response. What I have to do is define pipelines of operations that will help me answer the query. And here in my complex figure, I have the main phases that such a pipeline can have. Okay. And it can vary, of course, depending on the type of question that I want to answer, and as I said, the type of data. So in this kind of paradigm, what I start with is with not facts, but with raw data, these observations that are coming from the harvesting phase of the data cycle. Okay, so I have my raw data, and then the first thing I'm going to do is decide whether I can use it or not to answer my question. And this implies that I have to dig into the data and try to profile the content. What information can I get out of this data? And this is called a quantitative profiling. Okay, so the first thing I'm going to do facing a raw data collection is determine what are the data that are contained in this collection from a statistical point of view. What type of data do I have? Is it continuous? Is it not continuous? Is it how do you say this? Fact, I mean, not facts, it's descriptive or what, okay? So do I have missing values? What is the distribution of the values do I have? Do I have null values? Do I have outliers within these collections? So you see, it's all the statistical and quantitative profile that I have to start with respect to the data, okay? Then out of this and out of the possible knowledge that I might have from the context in which these data are produced, so it's different if I'm observing energy consumption than traffic than retail or whatever. So the next step is that I'm going to try to define the strategy to clean, normalize, engineer attributes, etc. And in order to do that, I'm going to use a lot of visualization. Graphs, graphics, plots that will help me observe the properties, the mathematical and quantitative properties of the data, okay? And eventually interact to zoom in or zoom out the understanding of this quantitative profile of the data so that I can figure out which will be the best way of cleaning, normalizing, or engineering attributes of the data. And then the third aspect that I have to decide is whether I'm going to use the whole bunch of data that I have, or if I'm going just to take a sample of the data. And if in the case that I'm going to take the sample of the data, how am I going to build my sample? And of course, you have guessed that I'm going to rely on statistical methodologies in order to make all these decisions. And this is called data exploration and preparation. So it's the first acquaintance that I have from a raw data collection that will help me, in fact, determine whether this data collection is useful and can be, in fact, yes, it's useful to answer some analytical query. So if I want to predict, for example, I can go to the data and explore it and say, is it possible out of these observations to predict the behavior of the phenomenon that they represent or not? And if I decide that it is possible to use this data in order to answer some research question, then I am going to go into the matter and then decide, depending on whether I'm looking for insight or foresight, which are the types of strategies that my pipeline will include. I have a sample, for example, am I going to fragment the sample in order to apply some model or not? And how, if so, how am I going to fragment the sample? Am I going to use generative or discriminative models in order to answer my question? And there you have a huge family of techniques, as we have enumerated them at the beginning of the session. Am I going to use descriptive statistics, inferential statistics? Am I going to use machine learning, artificial intelligence, or whatever method I can invent, and in order to answer my question? And an important thing in this phase of the pipeline is that I have always to assess every step and every result I get out of each step, okay? And this is called error analysis and ablative analysis. So I have to estimate to which extent the decision I make creates some error. Because as I said, we will never have a complete answer because we never have a complete observation of the phenomenon. And once I get results, again, I have to validate them and not only give a result, but give all the explanation that in which I obtain this result. And this is ablative analysis. So if I come back to the paradigm, the data are observations of phenomena. The queries have analytics objectives and are expressed as pipelines, as the one I have here. And the result is not data. You see, in my previous example, the result, if you go for Google or a Google query, it's a set of items, no, a list of items. Here, my result will be a model or a prediction that has associated assessment indexes, that is never definitive, and that has an error, a margin error, and it's normally accepted by comparison. What happens is that I have a question, I design a pipeline, I perform my pipeline, and I get this error with its error, a result with its error margin. Then I can apply an alternative method and see whether I get less error, and so on and so forth. And I determine which is the degree of error that I can accept in order to consider that my result is valid. Okay. So it's sets of pipelines that I'm going to apply in order to answer one research question. Okay. And again, it is associated with a quality of the result determined by a margin of error. So quite completely a different strategy than the one we have addressed in other exercises. So what we are going to do in this course is exactly this: learn and show examples of pipelines used to answer specific research questions. And again, point you towards the good strategies in order to define eventually your own pipelines, because for those that have arrived a little bit late, the idea is to make sure that at the end of the course, I give you a data collection with an associated research question, and you are capable of designing the pipeline that will help you answer the research question using technology, okay, data science technology. And because we are beginning to dig with this, and because we do not have access to huge computing resources, this will be done in a laboratory context, okay? So we will not go towards deployment, we'll just remain in the lab, inside the walls of the lab, and provide first solutions, not deployment solutions. So before, so it's 15:28. So before I go further with other part of the content, what we're going to do is we're going to have a coffee break, and we will come back at 15:30 to continue this session. So I'll let you grab a coffee or something and then come back in 10 minutes. I will do the same. Yes, we start the recording. Those that have arrived later, the video of the session will be available just afterwards the end of the session. On YouTube, I will send an email with the link. If you missed part of it, you will have it there. What else did I wanted to say? Oh yes, I also shared the link for the Google Sheet so that you can confirm or add an email address that you read and that I can use in order to contact you for providing material and other things. So do not hesitate to fill in the Google Sheet so that we can keep in contact, and that we will be tuned on the lectures and activities that we will organize. So until now, we have this defined datification, we have defined the characteristics and properties of big data collections. We gave the definition of big data, saying that you have to reach the limits of architectures, databases, and so on and so forth in order to be really talking about big data. We have talked about the two perspectives in which data can be queried. One is the classical one with facts, with databases that represent facts, and that can be queried directly in order to get information, and the type of queries that we will address in here, which refer to data collections that contain observations of phenomena, and the purpose of the querying is analytics, or either modeling or predictive, and the results are models with certain degree of validity defined by the estimation of the error that some result can have with respect to previous knowledge or other references. Okay, so, and of course you have understood that the objective of this
of this part of the course is to learn how to define these pipelines that implement the queries that will address this type of questions. With this, now we continue, as I remind you, we continue digging on the characteristics and things to consider with respect to data. And we have talked a lot about data, but we have less talked about the consumption perspective of data. And when you consume data, you have to consider other characteristics than the ones I described previously. Of course, that's something that we have said several times. So data consume data come in different sizes. But when you're a consumer of the data, you have to decide, given a data collection, which is the part of the collection that you are going to consume or to use, okay? When people share data collections, in fact, they do not share a big bunch of the whole collection. In fact, what they do, and given that the data collection, as we said, is a living entity that where many data come continuously. So what data collection owners share are releases of a data collection. And the releases have different sizes, which is very good because if we do not have access to a lot of computing and storage resources, we might decide that we're going to use a reasonable sized version or release of a data collection. And then eventually when we go out of the lab, for example, then we can decide to use a larger release, okay? If you are familiar, for example, with Wikipedia or with Stack Overflow or with, for example, Facebook and this kind of environments, for example, Wikipedia shares its content. And the idea is that these releases that are dated, so the release 2020, 21, etc., have different sizes so that people that want to explore their content and do some experiments on it can decide which is the size that best correspond to their conditions, okay? So this is why here in consume data, I'm talking about sizes, different sizes, because there's the notion of release, okay? Then of course, consume data come in many different quality status, uncertainty, and ambiguity degree. So as I showed in the preparation phase of a pipeline, you have to be aware of this, either because you know it or because there's a description of the data collection, or because, and in fact, because you did this exploration phase where you profile your data. Of course, there's different completeness, different production conditions, and the conditions in which it is retrieved. When you do analytical querying, it is not enough to know, to have access to the data, but you have to know the conditions in which data has been collected. This, for instance, for people working in addressing social problems are familiar with this. For example, if you are going to respond to queries regarding the degree of security and of security and the dangerous level of sectors in a city, you have to be aware in which conditions you collected data about this type of
of situation, because otherwise you might have a partial observation of the situation and then come to biased results. So this is important to consider. Then, and this goes to the next aspect, whether there are explicit cultural, contextual, or background properties that should be considered about the data. For example, if you want to profile the citizens of a city with respect to data coming from a social network, you have to consider that not everyone uses social networks and not everyone has access to smartphones, for example. So if you want to conclude about consumption situations or about behavior of the civilians, if you only consider the data from a social network, you're addressing an elite sector of the population, which might be even reduced with respect to other underrepresented population that you are not observing because they do not have access to this kind of technology, okay? Or less access to this kind of technology. So this is important to consider when you consume data. And then, well, when people work in academia, they tend to think that all the data are available like this and that there's no restrictions, but in fact, there are access policies towards data. We have to be sure that we know such policies. Then when we develop, is the audio good? Because I opened my AirPods and I'm not sure, but I think you do. Okay, so you have to consider also the results, the consumption of the results you produce when you design a pipeline. And the questions here are reproducibility. Since we are in an experimental context, reproducibility is key and very important, okay? When we announce the results of some query, some analytical query, we also have to make sure that our experiment is reproducible. Otherwise, no one can confirm that what we're saying is valid and the conditions in which the experiment was performed, etc. So reproducibility is key. And then we have also to share and define the degree of transparency. This means that all the decisions that we made in order to design an experiment must be explicit, okay, at some degree, depending also on the type of experiment or whether we have right to share some information or not. Today, for example, in the area of artificial intelligence, this is called explanatory algorithms and experiments, and this says explanatory artificial intelligence, which means that, and this is discussed also in media, we know algorithms, they produce results, but we do not know what is behind the algorithm, okay? So the idea is to be transparent and give enough explainability in order to determine in which conditions an algorithm produces some result. And this is in the case of an experimental pipeline, it's the same. We have to have logs of all the decisions that were made for each step of the pipeline so that this can be shared and that people consuming the results can understand the context of these results. So it's a very laborious exercise. It's very interesting. It can be very fruitful for an organization, for a decision-making process, but it's very laborious and very precise and rigorous thing to do.
Okay, so, and of course, what happens with respect to this is that when we get raw data, well, they are neither manageable nor explorable as such, because they are there's a variety, the volume, the veracity, the velocity, and the value associated to them. So we have to consider this within the design of our path. Now, the question also is, when we are finally using data collection, and we have the right to use the data collection, the type of questions that we as consumers have to ask ourselves is the data clean? If not, what has been done in order to make it clean? What information is available in these collections? Are there relations between data collections which could be exploited for better predicting situations? What are the update rates, and in what way does this affect the collection? Again, the collection is live, it's living. So if the collection evolves, are my experiments still valid? Or technically in terms of the design, but also in terms of the results they produce. And this should come together with the design of the experiment. So I had a nice animation here, but I didn't use it. Okay. So all this maintenance of the collection with all this description, again, this is a part of the jargon, is called data curation. What happens is that there is in the phase where you have harvesting and cleaning and preserving, in these two aspects comes curation in action. You're going to maintain and tag and explain and say what happened with the collection, in which conditions it was used, produced, etc., in a data curation cycle. So why? Because data collections are not used by one user for answering one research questions. They are there as observations of a situation, of situations, and they can be used to answer many different questions in many different contexts. So you have to enable the discovery and retrieval of collections, maintain the data quality. So if they have been cleaned and new releases come, they should be clean, maybe in the same conditions or in different conditions. And if it is different conditions, you have to say it, add data to describe this. Add value to the data and provide the reuse over time. Okay, so this is a parallel cycle of the data collections that come together with data science. We will see in a minute how it is concretely implemented in existing solutions. And it is there enabling people to run experiments. Now, what is important also to consider when we observe this data curation phase is that it is also important to know that you're going to keep everything. And this is why the approach is very costly in terms of resources. You don't want to use your raw data because cleaning it under different situations is adapted to respond specific questions in specific experiments. So you do not want to lose track of the initial collection that can be used for other purposes, okay? So considering this, you are going to have this spectrum of data where you have the degree of rawness of the data. So for a given collection, you can have different degrees of rawness, and you can decide, depending on your query objectives, which is the version that you are going to use. Is it the raw version or a more curated one? Okay. And regarding the query objectives, as we said, it is a spectrum that goes from exploration, just for understanding the content, towards foresight, including different versions of the data. And then once you have this, at some point, the data can become facts. And when you have facts, then you go to the first paradigm that I introduced and that we all know in querying, which is relational aggregative querying or information retrieval, as the queries we perform in Google search engine, for example. Okay, so once you have done a lot this, a lot, the knowledge becomes facts, is transformed into facts, and then you have the classic solutions on top of very, very, very curated versions of your data collection. And which is best? No one. It depends on your requirements. So again, in an organization, you will have all this spectrum of solutions in order to target different requirements and different queries, of course. If we go back to data curation, so as you have understood, you have to maintain all this spectrum alive, all this spectrum alive. And so there are solutions in order to make it possible for an organization to deal with all these versions of non-curated towards curated data. This is done through a data curation workflow that starts wrangling the data by selecting which is the data that you are going to archive and keep, vetting the data to understand, like data, like mining, no? Understanding which are the layers of data that you have, and then collecting, preserving and describing, and then grooming and provisioning, and like this. So normally today, I'm sure that if you have worked in organizations, this data curation workflow is implemented by data lakes solutions. Okay, so lakes are spaces of versions of collections in different curation degrees maintained on, through these workflows, and that are then used in different raw states for different purposes. And so there are systems that manage all these for an organization and let you, for example, implement experiments from different collections and versions and releases. For example, if you have such kind of situation, imagine that you are in a city, that you have many different collected data from traffic, from the use of alternative transport media, from interest points within the city, etc. So all the life of the city, and you have all this information, and this information can reside and come from many different stores, etc. And so you have a kind of lake with all this. Okay. So the first thing that a curation workflow would do is describe this messy content. Okay, and in order to describe this messy content, all this information that I'm referring to, like the conditions, the type, the uses, etc., is described through metadata. Okay, because the important thing to notice is that you want to deploy semi-automatic solutions in order to exploit all this. Okay, so it is important that you treat the descriptions as data, and that they are structured and managed and so on and so forth in order that they can be exploitable. So you're going to have such things Then you can also add your results of the data exploration phases and provide quantitative metadata associated to your collections. And there are solutions already by systems that provide you with this. For example, in the case of a system called MongoDB, which is very famous, in fact, what you have is for every element of your data, you have statistics of the distribution of the values and the missing values and so on and so forth. So this kind of thing of widget you can have in order to know what is contained in these data lakes that are curated by some system. There are more ambitious solutions because here, and nobody has reacted on these statements that I'm providing here in my infinite talk, is that all these data are quantitative, but I never talk about the real content and meaning of the data. Okay? So there are people that are interested in describing the semantics of the data. And so they provide approaches and solutions in order to try to interpret the semantics of the content of the data. Of course, because otherwise you have, like if you observe the log of the web or a web server or the log of a sensor collecting data, well, you see a lot of values, but unless you have the description of the meaning of each attribute, you don't know anything. You just know that there are values. Okay, so if you can complete this information with semantic information, of course, your exploration and your interpretation and exploitation of the data will be more accurate and maybe more interesting. Okay, so there are people that together with all this description, they add semantic description. And so they have these lakes of data with, and they extract all this information in order to complete as much as possible the description of the data. And so the process of extracting all this, of course, you have guessed, can be automatic and semi-automatic. So there are levels where you have automatic extraction, for example, everything that is quantitative and that has nothing to do with semantics can be done automatically. And once you go through more semantical solutions, there in many situations, you need the intervention of humans in order to tag the data with descriptions. And some like 30 years ago, something like that, people said, but who is going to accept tagging semantic with semantic metadata, the data? Nobody, this is not feasible. And then social networks appeared and we all contribute to this. Every time we tag the faces of people appearing in photographs, providing a lot of information on our activity in a social network, what we are doing is tagging semantically the information. And so the companies have semantic tagging of our information and can provide us with more interesting recommendations with regards to the data we tag. You see, so it's human and it's possible and it's feasible and it can be used in order to maintain collections. So for this result, I'm not going to go through it. This is really for completing your the perspective of the solutions. And of course, there are many different strategies. I will not go into detail with this, but depending on the level of metadata that is used to describe the data collections, you have different principles, advantages and disadvantages, and strategies and proposals in order to do such type of activities.
And then with respect to curation, this is important. This is a little bit, this table is a little bit old, but today the major database companies provide solutions with data lakes. So they are the data lake solutions from Microsoft, from Amazon, from Oracle, from all the big companies that have traditionally provided solutions to manage data with these data lakes solutions that help do what I have described in the previous minutes. Okay, so they are there, they are aware of the importance, and solutions exist for this. And now, where do we put all this? Because this is very nice, but this requires a lot of resources. And some years ago, like 10 years ago, the things that we are aware, and organizations are aware, that it is impossible for all organizations to have access and to maintain computing resources. When I mean computing resources, I am referring to execution cycles, so CPU or GPU or whatever cycles, computing cycles, storage, and main memory. Okay, so it is impossible to have all the resources necessary and extensible at our own wish. Okay, so there are architectures and solutions that started to emerge in order to externalize the access to these resources so that we can implement these cycles of management, of costly management of the data and exploitation with without having to buy thousands of disks, etc., and so on and so forth. Okay, and this here comes the notion of the cloud. And it is important that we, in our environment, are acquainted with the cloud, particularly because it is a very popular solution, particularly for executing costly experiments, data science experiments. And second, because we ourselves are going to use this solution, as I said, for those that joined the session later, because it will be practical. We won't need particular computers or whatever. You will just need your browser running in some device, and everything will be externalized, and we will still do data science experimentation. And because this is the way normally people do in real conditions. So just to make sure that we are all on the same page when we refer to cloud, the cloud is an architecture. Okay? It's an architecture that provides many different resources under the notion of service. Okay, so the coin of exchange of the cloud resources is the notion of service. When we talk about service from a computational point of view, we are talking about a hardware or a software entity grabbed with an application programming interface that is accessible on some network communication platform. Okay. For example, the internet. So set this, the cloud as an architecture will provide, organizes its services into 3 layers. And these 3 layers are the so-called reference architecture of the cloud. The 3 layers refer to services that have to do with the hardware, okay? And this is infrastructure as a service, okay? Here, infrastructure as a service. So here it's very reduced, but we have CPU, main memory, RAM, and disk resources as services. And CPU is one of the things. We can have GPUs, TPUs, TDUs, a lot of computing devices with different characteristics and different computing power accessible as service. Okay. So once we solve the infrastructure, then we have access to platform as a service, which are horizontal frameworks that we use in order to build applications. For example, compilers, for example, database management systems. So everything that we need in order to build systems, okay? And so these are platform as a service. And then at the very top, we have functional software, which is the layer of software as a service. Example of something that we use in these conditions. You might use Dropbox or Google Drive. What they are proposing, the providers are proposing, is a vertical cut of their services. They are providing us with storage support, disk. So there's somewhere in the world, hardware, disk, that they are providing us in order to store our files, our data, okay? Then, in order that we can go through the files, we need a file system similar to the one we have in our computer. And this file system that manages all the organization of the data stored in the disk is a platform as a service. But in order to avoid using the terminal and accessing the file system or our files, like in Unix or whatever, you know, with operating system operations, they provide also a third level of service, which is the application that we install in our computers, the Dropbox application. And the Dropbox application, which is a service, a software as a service, connects with the platform, which is the file system, and the file system connects with the storage support that stores our concrete files. And we have all these solutions externalized in in the Dropbox or Google Cloud. Okay, so this is an example of the way we access to externalized solutions on the cloud. Okay, so they of course can be more complex depending on the purpose. For experiments, it becomes a little bit more complex, but it is like this. So beyond experimentation, the idea is that we can evolve in our requirements. So at some point we have a disk storage available for some gigabytes or terabytes, but then suddenly we start producing more files and storing more files, and we need more storage support and so on and so forth. And the idea of the cloud is that it is elastic. So if our needs increase, they will provide with more resources. And if our needs are reduced, then they reduce the provision of the services, okay? And how is it controlled? Well, is it controlled with respect to an economic model known as pay-as-you-go? So what will determine the unlimited access to these kind of resources? Our credit card. So if we have some subscription with some amount of money, we have access to some resources. And if we want to increase, well, we put more money and we have more and more and more and more. The limit is normally the credit card, okay? And again, it can be reduced. Anyway, this solution, this externalized solution, provides us with ready-to-use environments
for storing big data and running greedy processing tasks, as the ones we are going to require to run for data science experiments. Very nice. This solution is very interesting. We'll see. Now let's go and have a look to something concrete. So the cloud, I mean, at the beginning it was simple, and now it has become a little bit more complex, and it has, cloud providers have personalized their provision of resources depending on the type of use, the type of user, etc. So now the access to the cloud is much more personalized and diverse in a sense. So of course, when data science started to consolidate as an important task, the providers started to propose solutions devoted concretely to data science experiments, okay? And these solutions are called data science or data labs, okay? And they provide services adapted to the type of tasks that we have to implement when designing and executing experiments. And this is what we're going to see now. Of course, you have guessed there are many solutions and many providers. We are going in our context to use Google solutions because they are easy to use, and because they, almost all providers, but they are easy to use, and also they are free. Okay, there's a part of free access to them. Of course, if we want to scale, they are not free, but for our purposes, they are free. So the first thing that we are going to see into concrete solutions is the part of the data, which is the part that we have been discussing in this session. So in order to deal with the data under this curation spirit, providers have come up with this notion of data labs services. In general, the architecture of such a service looks like this to the left of the slide. Your data, you have guessed, and you know this, can reside either in your own disk, personal disk in your machine, or it can rely in, it can lie in a storage support, in a storage service on the cloud. For example, let's put Dropbox, or let's think about Google Drive, okay? Or OneDrive, or this kind of storage solutions, okay? So they can reside on the cloud or on your disk. Then, as I explained before, you will have a file system that will help you access to these storage supports. Normally, as I said, the providers will have this included as built-in service in their solutions. Our computers have a built-in file system already packed when we buy the computer. And if we have the cloud providers solutions, either we have an app or something that gives access to the file system. Then, depending on the degree of distribution, for example, in our local computer, there is one disk or at least two, but in an abstract manner, the operating system shows us one integrated version of the storage support. So the file system is not distributed. But when we access the cloud, in order to ensure availability, creates copies of our data, and it distributes them across different data centers, so that geographically distributed or not, in order to ensure availability, okay, and durability. So our data are distributed, and so they provide with distributed file systems in order to let us access the data. Okay, so this is the lowest part of a data lab service. Then you can have access to other data management stores that access the data under more querying like solutions. And you can also, through programs, access the data. Okay. And then at the very top, you can have also solutions in order to version your data collections. As I explained, you don't have only one version of the data, you can have many releases, and you can have versions of it. And then the system will provide you with these versioning managers that help you to deal with all these different releases. And they also provide tools in order that we can tag our data with metadata that will describe the content and that will reinforce the curation process of our data. So I'm going to show you how does it look like in the Kaggle solution, which is a solution from Google. And then for the next time, I will give instructions in order that you can create an account and start using the tool for some for exercises that we are going to run. So I'm going to connect, and then I share my my browser so that you can see how Kaggle looks like. So I'm going to stop sharing and then share again. Share this. Okay. So this is the data lab of Kaggle. It looks like this. So as I said, it is a browser interface. So the address is kaggle.com. Well, here is me, I have an account. And so Kaggle will, is not only a data lab, it is also a data science lab, but we are going to first have a look at the data lab version. So it works as a kind of social network. For those that are acquainted to, for example, Stack Overflow or similar social networks, what happens is that users create accounts and connect, and they provide content, and other users have access to the content, and it works like reputation. So if your content is very interesting, you have stars from users accessing your content, and you acquire into reputation, and you can your content and you as a user can have can become popular or not, depending on the reputation. Okay, so this is of course not new for you. So it works like this, and it provides many different things. The idea is to create communities that address data science problems through experiments based on data. Okay, so the first thing that that you can see is that you can have this famous data lab, and what happens is that you can either have access to existing data sets shared by people, or you yourself can create data sets that you can decide whether to share them publicly or not. Okay, so let's have a look at a data set. I don't know, let's choose this one, whatever. So the data set looks like this. You have, of course, like kind of metadata, the owner of the data collection. the person has given a title on it. You can see that the person updated the first version an hour ago. And then you have the degree of usability of the data. You have the license, so the rights to access the data. You have tags, so metadata describing the topic of the data. So here it's about automobiles, vehicles, and data visualization. The owner can also provide a description of the content of the data. And then you have the format. So this is a CSV file. A CSV format is a tabular format. Yes.
Sorry to interrupt, but we cannot see your screen.
Sorry. Thank you for telling me. I'm going to stop and then share again. And here. And now, I think you can. Do you see the browser? Yeah. Thank you. So come back. You have the data set, you have the title, you have the owner, some information about the version. Then you the system estimates the usability of the data. This is done automatically, okay? So you upload the data and then the system goes through the data and determines the usability of the data. You have the license, the tags. This is provided, of course, by a human. And then, as I said, you have.
Excuse me.
Yes.
Sorry, it's black again.
It's black again.
After a few seconds.
I think that I have connection problems. So I'm going to give you the link. Is it like this? Again, stop and then share again. I'm going to stop moving, maybe. There you have it. No?
Yes.
Okay, so this is the format. So you know that the data set is 500 kbytes, that it is in a CSV format, so it's a table like Excel. You know the number of columns that contains the table. It is provided in one file. You have the statistics of every attribute in the table with the distribution of every column. I'm just trying not to move a lot so that okay. So this is for it says that it has been downloaded. Oh no, that's the size, and it also says how many times it has been downloaded if this is the case. Then it went back, but I've learned the lesson. Then it can describe whether people have used it. It goes out again. So if people someone has used it to perform some experiment, if such, there is a code associated, whether there is code associated to it, whether there have been people discussing on the content of the data sets. So you see all this kind of information that, as I have described in the curation cycle, that complements the raw content of the collection. And so in this solution, as I said, with respect to the data curation cycle, is that if I want to use, I am looking for a data collection, I can use Kaggle and in search, say, well, I am looking for data collections about energy and household energy, and then it will provide me with collections that are associated to this topic, and then I can use them. I can create new versions. I can say that I created an experiment and so on and so forth. And so in this way, not only the collections are there, but they are enriched with the metadata provided by the owner and by other people that could have used the collection. Okay. And all this information serves as curation information in order that people can exploit this data. Okay. So as you can see, these environments, of course, I have described the general view of the whole spectrum of the possible solutions. Here you have a concrete solution, which is very popular, practical, etc., and goes in the sense of this trend. If you are in an organization, you would have a similar solution, but maybe in a private context with respect to the vocabulary of the organization, with respect to some rights, depending on your appartenance to the organization, etc. But it would look like this, and it will serve as a laboratory in order to maintain your collections. So far, more or less good, because as you can see, what is the critical aspect with this externalization solution? It's great, it's complete, it's elastic. The critical element is connection. Okay, everything is fine as long as you have enough bandwidth in order to access all this. Okay, so this critical aspect, of course, is an open issue, but more and more, of course, we now experiment this. We have the fiber, we have many different options in order to ensure this connectivity aspect, so that these externalized solutions can work as well as possible. In the case of the lecture, as I said, we're going to use Kaggle. I will give some examples with Google Colab. I tend not to use Google Colab because this requires you to have a Google Drive space, etc. And so it can be problematic. So this is why I use Kaggle, but Google Colab, it's a more technical thing that can also work in order to do experiments. And as I said, almost all providers today have this kind of solutions in order to deal with data science problems. So hands-on will not be today, it would be the next time. Just let me control them. Hour, so I have, okay, more or less than an hour. Okay. So do you have reactions, questions about this? I don't think so. Well, I suppose not, because we haven't touched anything. And as long as we start touching, then I might have more reactions. So I'm going to touch the last part of the introductory part for am I sharing? I'm sharing the browser. This is good. So I'm going to go back to the content. Let's see if it shows the content. So with regards to the content, I have introduced data-centric sciences, principles and common aspects. Of course, I had the introduction, which is big data and datification. Then we have addressed the profiles of digital data collections with their characteristics and properties. And we have started to dig into the characteristics of the collections and the data lab notion. And now we are going to address this part, which is what are the tools or the algorithms that can be used in order to, as third element of the design of experiments, okay? So that we can be ready to start with the design of experiments the next session. Oh. So let's go for it. Big data, data analytics algorithms and tools. In order to talk about this, we have first to formally define the notion of data science, okay? So it can be defined as follows. It's a methodology by which actionable insights can be inferred from data. So the characteristic, well, now of any modern science, but of data science in particular, is that it is a complex, multifaceted field that can be approached from several points of view: ethics, methodology, business models, how to deal with big data, data engineering, data governance. So it's a kind of chimera of solutions and methodologies of different sciences and put together in order to provide experimental solutions on data. The objective is to produce beliefs informed by data, okay, which is what I said when I described the purpose of datification, is that all decisions and conclusions and so on and so forth that we produce should be based on data. And then in the absence of, why? Because in the absence of data, beliefs are uninformed and decisions are based on best practices and intuition. And in our historical moment, this is not a very strategic way of behaving. If you have seen, for example, the news regarding pandemic, for example, as you probably saw in the news that one of the previous Minister of Health here in France is being pursued because of her decisions made with respect to pandemic at the beginning of the pandemic. And the idea is that she didn't consider all the variables that they had at that moment, and the decisions were not very accurate, as the imputation say. There are solutions and intentions in order to avoid this kind of problems by tracking all the provenance of the decisions made by politicians based on data, okay? So the idea would be that you show which are the data that you used in order to make your decisions, and what was your reasoning, the line of reasoning that you perform in order to achieve some decision, okay? So this is the promise of data science, but I mean, we can discuss of whether this is valid or not, but this is the promise, and this is the spirit of the type of things that we are going to perform. So set this. There are, well, okay, it's multifaceted, it's a chimera, and what does it use? Well, the basis of the strategies of data science is that it's going to perform probing reality, which means that data can be gathered by passive or active methods. And if we use active methods, data represents the response of the world to our actions. What is the best button size and color of some interface? The best answer can only be found by probing the world. So we all know that, I don't know if you're familiar, but Facebook at some points when you use it a lot, it provides you with alternative interfaces. And then for some days or weeks, users use this new interface, and then they get feedback from you automatically or directly to determine how to make evolve their interface and put it as a global interface for all the users, this kind of thing. So you probe reality in order to get your data and then use it in order to make decisions. So that's a first strategy that is very popular when you design the data science solutions. Then another strategy is discovering patterns. So the idea is that datified problems will be analyzed, preferably automatically, to discover patterns, natural clusters that simplify solutions. For example, profile users is critical, and so the idea is that you are going to observe the behavior of some set of users and then try to identify some behavioral patterns, okay, and decide something. And this is also for citizens. For example, you can decide how citizens evolve within an urban space and then decide where to put a gas station or a shopping mall or some road, for example. Okay, so you're looking for patterns that can guide you to understanding some phenomena. Then, as I said, predicting events, traffic or whatever, that I have given many examples. And then, of course, understanding people, understanding natural language. So I'm sure that you are acquainted with this digital assistants. So the idea is that as much, I mean, you use them very much. So the assistant using your natural language, you will ask questions and the assistant will help you go through information or whatever. So these strategies are the most common strategies that data science uses in order to address problems. And now this is the story of workflows. So everything is a process, everything is a workflow that operates on data. So the data science as a science has its particular workflow in order to address, I mean, describing its methodology, okay? So the idea is that you are going to, I'm going to start here to collect and harvest data. You are going to explore it, maybe using visualization methods or any other method. You're going to clean and transform the data, and then you are going to obtain models that describe the phenomenon represented by the data. Then you are going to validate the produced model, also using visualization exploration tools, or even validating by transforming and by applying other models. And once the model and the result have been validated, then you can deploy the solution as a real solution that you are going to communicate, and then you are going to understand some phenomenon. And out of your understanding and the interpretation, you will have of your understanding, this data will be collected and so on and so forth to the infinite. So this is the method adopted by data science. So we are not going to do the hands-on now. As I said, well, it is a real chimera, okay? So some people say that it is not even a real science, but it's just a conglomeration of solutions that come from many different areas. Of course, you have computer science with different moments and milestones and results that are there providing part of the method. I'm feeding the part of the methodology of data science. You have data technology, you have a lot of visualization, you have a lot of mathematics. Okay, I mean, if I would, someone would ask me, which is the real backbone of data science besides data, it is mathematics. Okay, no mathematics, no data science. And particularly, of course, statistics, which is part of mathematics. Now, and solutions come from the first moments in history until later, okay? And all this is integrated in the methodology and in the workflow that I have described before. Now, if we go concrete and we say, what are we going to do for the experiments? As I said, we're going to use mathematics and statistics in two different senses. Because we are going to apply statistics and mathematics and numerical models and all the mathematics that we know in engineering in order to address problems, plus algorithms and solutions provided by machine learning and in general artificial intelligence that themselves are based on statistics and probability. Okay, we will go through some examples of algorithms and we will see that the very background of the heuristics provided by these algorithms are based on statistics and probability. So in these two senses, mathematics and statistics and probability will play the key role in data science. Then, of course, there is computer science and IT in all its extent, because this is done on computers, and because it is then, it uses digitalized data, etc. And then other aspects that we won't touch here, but that are there, is that at some point, of course, solutions and algorithms are very nice, but they have to be embedded in real software that is used by many. So software development is there in order to package the solutions and then make them accessible to everyone. And of course, domains and business knowledge. Domains, because the experiments are related to particular disciplines. So the knowledge of the discipline plays a very important role in order to perform the experiments and all the whole workflow of a data science solution. And then business, because once you touch the delivery of a solution, you are there with a business model in order to sell your solution and get return of investment out of it. And why? Because running, I mean, I've shown that it is laborious, that you require to buy computing resources. Of course, you need human resources. So this is an investment. And people, companies and organizations that are investing in this must be sure that this investment has a return of investment. Otherwise, there is no point of doing this. Okay, so this is the aspect to be considered there. Now, the principle that is used is that the patterns, of course, there's the degree of error and the interpretation and but in order that they are really useful, they have to be valid, they have to be useful, they have to be unexpected, okay? So there is no point to get to conclusions that everyone can see. Okay, I see that you have four chairs in the room. Of course, we knew it. I don't know if you have seen there's an article running in social networks today and yesterday that says that there's some artificial intelligence that concluded about the properties of real numbers. Okay. Well, good for people that are developing the algorithm, but this doesn't contribute to our knowledge or to our usefulness in any way. We know the properties of real numbers. Do I have a question? Okay. So they should be unexpected and they should be understandable, okay, so that we can learn out of the conclusions driven by our experiments. Now, something that has been said implicitly in this, in the workflow that I presented regarding data science, but that it's has not been said implicitly, is that the experiments are done in the system backwards. Okay, so this means that they are done step by step and under a test and learn procedure. Okay, so an experiment is not set and run in one shot. Every step, I mean, you really run it step by step, and you will see that very clearly in the experiments that we are going to design. And then, since there is a lot of parametering, adjusting to the data, to the algorithm, to the conditions, to the results, etc. So you test and learn a lot. Okay? And this is a very important critique that receives data science in its methodology, is that, I mean, not extracting generalization of the experiments implies that there is a lot of human hours invested and a lot of resources, okay? And so it becomes very laborious, costly, and you never have a general solution. So it's done artisanal, in an artisanal manner, and it is per problem solution. And this is not very interesting in order to scale and to for return of investment in general. But this is something that you have to be clear about. You will never run an experiment in a one shot and you will get a result and you're happy and you go home. No, it will take a lot of test and learn. That I said, we will use statistics, that's something that I said. And then let's go and start digging into the algorithmic part, okay? So when we will use statistics, the notions that we will borrow from statistics will be, of course, population and samples. You have completely understood, because in fact, our population is all the data collections harvested for observing some entity. And the question is whether we are going to use the whole data collection or a sample of it. People that have been working and that worked a lot and promoted a lot the promise of big data used to say that this is the real change with respect to classic ways of solving problems. That in fact, when we used to, in statistics, to use samples, etc., and particularly when we use computers, we needed to define samples because it was impossible for a human being or a computer to deal with all the data, okay, all the population. Whereas now, since we are rich in computing resources, we could use this, okay? But this is a question that is being addressed by mathematicians and people doing algorithmics in order to determine whether we should anyway continue sampling, etc., or really embracing volume and using all the collections in order to do data science. But anyway, we will still be using population and sample. And then from descriptive statistics, we will apply all the concepts that we know with respect to measures in order to describe the content of the data or interpret them, because in the previous, when I showed you this Kaggle solution, as you could see, the statistics are generated automatically by the system, okay? So in one shot, when you have a data collection, the system will go through the data, generate the statistics so that you can have the quantitative profile of the content of a data collection, okay? But anyway, even if you do not write code in order to perform such a thing, you will use the notion of distribution, of standard deviation, etc., in order to understand the profile of your data. And then, of course, there will be a lot of plotting that will be used in order to make the analysis, okay? So you produce the statistics and then you use tools, visualization tools, in order to perform the analysis of the data and make the decisions on how you're going to design your experiments. And then from inferential statistics, the idea is that you are going to state hypotheses and then apply the methodology of inferential statistics in order to drive conclusions with respect to a given research question. So the research question will be stated as hypothesis, as a statistical hypothesis, and then all the experiment that you will design will be devoted in order to contradict or validate the hypothesis. So this is the I mean, a general overview of the kind of concepts that we are going to borrow from statistics in order to design experiments. What did I wanted to say here? Yes, I mean, then this is something that I have said before, in order to drive the process, and particularly this kind of statistics will be used for the data preparation. I showed you in the data science pipeline. So you have the harvesting, the parsing, the cleaning, and all these methods apply to this. In fact, in order to go from a high degree of rawness to a data collection that will be prepared in order to be used, really used within an experiment, okay? So the result of the data exploration phase with statistics applied on it will be a data collection that will be really used in order to run your experiment. Now, what is the part of artificial intelligence in data science? Well, in fact, as I said at the beginning of the session, there are some situations in which, given the status of the data, or even the type of the format of the data, for example, if you're dealing with images, statistics cannot be applied. So when you have other types of data, or the status of your data is not well adapted, even if clean, in order to apply these sound and smooth mathematical methods, then artificial intelligence comes into the scene. Just for those that are not very acquainted with this classification of knowledge in computer science, what happens is that there's computer science, and then you have artificial intelligence that has essentially three or four main families of disciplines. You have the discipline of curating knowledge, the discipline regarding machine learning, you have reverse engineering, and you have that data mining, even if the community of data mining does not really appreciate to be considered as part of artificial intelligence. They consider that they are a discipline themselves. But anyway, all these solutions are delivered in terms of algorithms. Okay, so what they provide is algorithms, as I said, using probability and statistics in order to provide heuristics for classifying, predicting, etc. Okay? Modeling, etc. And they rely in a particular important manner on data, on input data. Now, this is just to say that at some point in the history of artificial intelligence itself and in data science, solutions were laboratory solutions, okay? Nobody used them. But since some years ago, there are real applications and solutions used by everyone. So you have robotics, you have intelligent and smart devices, cities, robotics, etc., where you behind you have this data science based on artificial intelligence that are there in concrete solutions in the market. So this is the part that I was saying, so machine learning, data mining, and databases, because databases address some aspects of aggregation that are sometimes present in to solve some of the questions on data science, and also because they provide solutions in order to intelligently manage data and be sure that solutions scale at runtime. In general, there are two cultures: the culture of data science and then machine learning and data mining people. Now, more and more, they have come together and they interact together. And in the class, we're going to address both. Now, the challenge with when you go from your fundamental knowledge of mathematics and you move into machine learning and artificial intelligence, even if we have here regression, is that there are thousands of algorithms. Well, some better than the other, okay? Everyone says that she or he has produced the best algorithm better belonging to any of these families, okay? So anyway, these are most popular families in artificial intelligence and machine learning that, that have produced algorithms useful for addressing data science problems. So if someone that would claim his or herself as a data scientist must be acquainted of the families and of the principles and characteristics of these algorithms. Even if today there are people, for example, that are specialized in clustering, and they do nothing but clustering, or nothing but neural networks, for example, because these are very complex ways of defining solutions, and you need to be very specialized in order about the algorithms, their cost, their parametering laws, etc. So people specialize in one of them and more and more. Okay. But if you want to have a general culture on the algorithms, at least you should know the families and some representative algorithms of each of the families. Now, okay, we have data. We have a very, very general overview of mathematical and algorithmic tools. And now how do we put them together in order to really set our experiments? In order to do that, we have to go towards computer science and see the families of data science toolboxes that are available today in order to execute experiments. Just let me check. Down. Okay. So, first of all, you have data and you have algorithms and tools associated for addressing data management, etc., and algorithmic execution. The problem is that when you want to perform experiments, both have to come together. And today there is a divide in solutions between those solutions providing data management solutions and those solutions providing algorithm execution. Okay. And more, when you want to use some tool, you have to be aware of the degree of divide implied in a specific tool. How do you do this? It depends on the amount of data, and their volume is important, that you are going to use in order to perform an experiment in a specific scale. Okay. So if you are working with your personal machine, you have to consider that the amount of data that you are going to, and you are going to run your experiments on your machine, you have to be aware that the amount of data that you can use in order to run an experiment should be small, adapted to the power of execution of your computer. Okay. And if the tool has very limited data management strategies, you have to be aware that almost all algorithms run with data in main memory. So if your main memory is never too big. So if main memory is not very big, you will be obliged to execute your algorithms in a very small scale. Okay. And once you want to scale, you have to look for tools that really have strategies in order to manage the data from these two memory in order to shorten the divide and be sure that you can execute your solutions. Okay. So of course, this is just culture. In a real organizational setting, this kind of knowledge would be associated to the data engineer of your organization, and you as consumer of data science tools and experimental environments, you will delegate these preparations, infrastructure preparation to the data engineer, and you would just care about the results and the interpretation and things like that. Okay, but be aware that the interest of having data engineering support is because of this. Now, how do we get all the tools necessary in order to perform data science experiments? Well, particularly if we are externalizing, we are going to adopt the hypothesis that we are going to externalize their execution. Okay, so the way we access, for example, cloud services is in the form of virtual machines. Okay, so many vendors propose already built-in virtual data science virtual machines that you can install and use in order to run your experiments. And there you have everything in the virtual machine. You have systems in order to harvest data and collect data. You have systems in order to, and solutions in order to visualize your data. You have libraries with the most common machine learning tools and artificial intelligence tools, so the deep learning tools. For that, you have programming languages well adapted to code your experiments. You have also development environments where you are going to code your experiments. So you have all these families of tools ready to use so that you can only care on the experimental setting and not on installing and so on and so forth. So this is a way of accessing a data science solution for as an environment in order to implement your experiments. Now this I'm going to skip because this is not important for us, but here, in fact, what you should know is that these virtualization solutions are not the only solution, and they belong to a family of tools, of toolboxes. Remember that we are studying now toolboxes that provide data science execution environments. So these toolboxes are called big data platforms or stacks. In fact, you have stacks of many different tools as services that are put together into these virtual machines. So either you use a ready-to-use virtual machine, or you have a DevOps support where someone configures your virtual machine, data science virtual machine, according to your requirements. So you will have storage, you will have platform solutions, you will have a platform, you will have data as a service, etc., function as a service, etc. All the things that you would use in order to build a well-adapted data science virtual machine that someone will use to run experiments. So this is a very technical solution, okay? But the thing is that when you are someone, I don't know, a retail manager or someone that is out of the discipline of computer science, you don't want to struggle with this configuration and complex thing to do. You need a lighter environment where you can test your ideas, and then once you are sure about what you wanted to test, experiment, etc., even to state your requirements, then you can give the idea to a data engineer or a data scientist, and then the person can face the technical problems, okay? So there are the so-called wide environments, which are environments that provide you with the with a programming language and some execution environments where you write very simply your experiments and you run them, and you do not care about other things, okay? So these environments can work on the web, so you don't even have to install anything. They are externalized, or you can also install some simple tool and then use it in order to define your environments. And the third type of solution is the so-called machine learning services that in fact address the data management and data execution and algorithm execution aspects through integrated solutions. And these solutions include, it's like having a friendly access to this kind of solution of big platform stack, okay? So most of the vendors use them, and this is in fact to go from this small scale to this to a large scale deployment of experiments with a lot of data, with parallel execution possibilities, etc. I mean, the scale grows much more, whereas here we are in the inside of the lab walls. And again, I have a very nice animation that I didn't use. So what we're going to do, that's something that is that for the course, we're going to use this kind of solution. Okay, a wide environment with all the necessary in order to execute experiments, but at a small scale. Okay, even if we are going to externalize. Okay, so with respect to, yes, change. With respect to the experimentation, what we're going to do is, of course, we're going to use a programming language. So I know that because of your background, many of you are quite acquainted with MATLAB and R. We're going to use Python because it's very popular, and this will give you another perspective of the experiments, but you will see that if you have used either R or MATLAB, the principle is quite similar. So you will not be surprised by anything with respect to Python. So there's also a discussion whether which is best than the other. I don't think that this discussion is interesting. Different communities are comfortable using these three solutions, but in the principle, it doesn't change a lot. Because what is important is the design of the experiment and not the actual tool in which with the libraries that you are going to use to perform it. So with respect to Python, in fact, it already provides, again, as you are used in MATLAB or in R, with the libraries necessary to do data science. So there are 4 basic libraries that are devoted to data science exercises. So the first library is NumPy that provides, it is based on the notion of multidimensional arrays, and it provides with basic operations useful in linear algebra, okay? I didn't say this before, but beyond statistics and probability, linear algebra is also an important tool when addressing data science experiments and questions, okay? So NumPy provides you with all the necessary, with all the linear algebra functions that we all know from our engineering background in order to operate on these multidimensional arrays. Then you have SciPy, which again, this is something that in engineering is quite popular, using numerical algorithms in order to address some problems. So you have all the methods implemented already for these numerical algorithms. And it also includes signal processing, optimization, and statistics. Then you have a very basic, even if there are also other libraries more fancy, but Matplotlib is the library, basic library used in order to plot, okay, for plot. Then, since we go towards more machine learning, I don't know why people associate regression to machine learning, but anyway. So there's the machine learning library, scikit-learn, that provides, again, with almost all classic algorithms or many different families or, already implemented there, ready to use. And then, as you will see in different data labs, many data collections are harvested and formatted as CSVs, as tables. Okay? So the Pandas library provides you with all the necessary operations in order to play with the tables, tabular data. Okay. So these are the basic functions provided by Python. Again, for those that have joined us right now, it's very similar to MATLAB or R. Now, everything, the question is, of course, it's a programming language, so you can write programs, okay? But the idea is that when you do an experiment, as I said, you go step by step. So people started to provide solutions in the sense that having some execution and some unit of experimentation writing that would be easy to use, done step by step, and then executed in a very simple manner. And they came up with the idea of defining what we call a notebook. Okay, so a notebook is a set of cells where you can have either a text or a code that you are going to execute step by step in an interpreted manner, and that you this will provide you with this exploratory notion of experimentation, where you are going to go through the data and prepare it and play with it and then apply some functions and see results, etc. And with these textual cells that will provide you with the opportunity to log as an experiment, which were the decisions and the results and the interpretations that you associate to your results. And this famous notebook is executed in a so-called integrated development environment that that gives you the execution environment in order to execute your notes. So this is what we're going to use. And of course, you have guests. Either you can install it in your machine or you can access through the web. So we are going to access it through the web. And when you access it through the web, it is called a web integrated development environment. So this is the acronym of WIFE, no? WIFE. So there are different solutions, of course, and the solution that we are going to use is Jupyter. And yes, we will use it, as you will see, on top of the data science service provided by Kaggle. Okay, so no need to install. So for those that are not acquainted with the notebooks, they look like this. So it's you have cells. This cell is a textual cell. This is a code cell, and you obtain your results like that. And what is interesting about a notebook is that you can exchange it and share it, and without need of doing anything. And you will see that when you use you can share it without even exchanging a file. So do I have questions until now? So we're almost finishing. So, and in fact, we have finished. Okay, so until here, we have the very general vision of what we will do in the lecture, and of course, what is done in data science. So you have the profile of the data, you have the profile of the algorithms, you have a vision of a general vision of the different tools that can be used in order to perform data science experiments. And this is the introductory part.
Okay, so from now on, what we will do is design experiments and play with a data science environment in order to run our experiments and see what happens for when we want to solve different types of research questions. Okay. So just to make sure, I know that I've been repeating this during the whole 4 hours, but please, those, if you, some of you haven't written your email address and your name, etc., in the Google Sheet that we share, please be sure that you do so that I can have contact with you, particularly because for the next time, I'm going to send you instructions in order to create an account on Kaggle, and so that you can be ready in order to do some exercises that we are going to perform during the next session in on Kaggle. Okay, so I remind you that both of the sessions are the theoretical sessions, but even if we are doing theory, we will combine it with some practice so that you can have a concrete relation with the theoretical concepts. So I think that I have the Google Sheet. Yes, I'm going to stop sharing my machine, my screen, sorry, and I will let me copy them. The link. Here you have the link for the Google Sheet where you have to put your email address and name, etc. And then, well, I will not share again the address of the site. What I will do is when I will contact you with the instructions with Kaggle, I will give again the address of the site so that you can access to the material. Okay. So I remind you that the next session is next Monday at the same time. You're welcome, Miguel. So if I'm going to stop registering.